Hi and welcome back. We are continuing our discussion on simple harmonic motion and waves. And previously we were talking about how to describe this simple harmonic motion in terms of equations. And let's now look at this in a more practical sense. Okay, so what am I talking about basically? So let's look at this first part. Okay, we're going to look all the way down at the bottom here. Okay, and in this middle part, this is we have a mass on a spring. Okay, and this here in this middle part is its equilibrium position. Okay, this means at rest, this is what the spring wants to naturally sit, or how the spring wants to naturally sit. Okay, that's how I think of equilibrium positions. What does it want to be kind of in balance? Okay, and say we take that mass here and we push it up to some length here. Okay, so they're calling this the unstrained length. Okay, so we are pushing the ball closer to where it's attached here. Okay, and we let that go. So now that mass is going to go down and then back up and down. Okay, so it's going to oscillate here. Okay, and through this oscillation you can see the maximum amplitudes, okay, as x, positive x, and then it goes down to negative x. Okay, so this is my amplitudes, and this is what we are trying to describe in wave, in these equations here. Okay, so if we take this and kind of, spread this out over time. So we've got a bunch of different diagrams here. So this is our start, and this would be our finish here. Okay, and we want to visualize that motion with some type of equation, okay, or a graph of this. Okay, so if I were to follow this position, even just looking at this image, okay, if I were to follow that position, I can see that it kind of looks like a wave pattern already, right? So if I were to take data points, okay, and say it's at this point at x at time 0, and then at this point x equals 0 at time 1, okay, and then continue that, I can plot this exactly, okay? So I can plot my position x versus my time, t, okay? Just like we were doing before in the previous sections of this course, but now we're looking at harmonic motion, simple harmonic motion, okay? So it's the same idea though, okay? Plotting position versus time, okay? And so this is what we come up with if we take a bunch of data points, okay? This is the idea, and this is a cosine function, and so this is where they come up with this equation here, this function equation, okay? And then the same thing with the velocity. We can plot the velocity versus the time to get this equation, and then the acceleration versus the time to get that equation. Okay, so this is what we will be looking at. All right, so with that, we also can define what a simple pendulum is. Okay, and that is defined to have an object that has some mass, okay, which is suspended from a wire or a string, okay, and this mass is, you can say that it's known as the pendulum bob. Okay, but really you just want to know that it's some mass, okay? And if you think of a pendulum, this is what we're thinking of. So if we let some mass go, okay, this guy's going to swing over here, and then it'll swing back over here, and so forth. So again, it has that oscillatory motion, okay? This small oscillation. And what we look at typically is going to be some kind of angle here. So we're going to be looking at this angle, and we're going to look at the forces, the tension involved with this angle. Okay, so let me rephrase that. So we're going to be looking at these simple pendulums, okay, where we have some kind of mass on a string, and we're going to hold it up at some angle and then let it go, and we can describe that motion, okay? And we need to note that when we're going through this, that there is some kind of restoring force. Remember a while back in this PowerPoint, we talked about restoring forces, okay? And this is typically some kind of mg times, let's see, I think it was sine theta? Yeah, sine theta. Okay, that would be our restoring force, F. But we want to note that for small angles, or about less than about 15 degrees, we can use this approximation that sine theta is about equal to theta. Okay, so this is called the small angle approximation. So just note that we do this, okay? And with that, we can go ahead and say that the force, the restoring force, is approximately, approximately minus mg theta, okay? So again, we are looking at our restoring force, okay? And the arc length, S, you can't see it anymore, but S equals L, which is the length of the string, okay, times theta, okay, this angle here. And so with that, we can plug that into the equation rather than if we didn't have the angle here, we can go ahead and plug this into the equation. And our restoring force F then would be about negative mg S over L. Okay. So okay, so looking at this diagram, because it's kind of probably better to look at it to describe what I just talked about. So our restoring force, remember that our systems want to be at equilibrium. Okay, so if they're not at equilibrium, they want to go back to equilibrium. Okay, so if we took a pendulum and put it out of equilibrium, there's going to be some kind of restoring force to try to get it back, right? And so that's what this restoring force is right here. Okay, that's that arrow right there. So that's the restoring force, and you can calculate it through some algebra and get that it is equal to negative mg times sine theta. Okay, so we can say, let's see, we can say this is theta. We know this here as the weight, mg, okay? So if I'm looking at this angle, this is also theta, and I say I want to know this force here, okay, so it's getting a little messy, but this force, it's going to be the opposite over the hypotenuse that I know, so it's going to be so. Okay, just kind of give you guys a background of how we get to this. Okay, so it's going to be sine theta equals my opposite, which is some force F, divided by my mg. And I'm going to insert a negative because I know that this is in the negative direction. Okay, So then my F is going to be negative mg sine theta, just like this. And so again, if this angle, so if theta is less than 15 degrees, I can say that the sine theta is about equal to theta. Okay, that's that small angle approximation again. Okay, so this is my restoring force, and we can also state it as this way. Oh shoot, I just crossed that one out again. F is approximately equal to mg over L. Just put a negative times S, the arc length. Okay, and we can use this information to then talk about the period of oscillation, and that is going to be T equals 2 pi square root of L over G. Okay, so that's how you analyze a simple pendulum, and we can go ahead and put this into use. Okay, so this is an example 16.5. It says, what is the acceleration due to gravity in a region where a simple pendulum having a length L of 75 centimeters that has a period T of 1.7357 seconds. Okay, so we're looking at the acceleration due to gravity, G. So what is G? Okay, well, we just found this period equation, so we can use that. So T equals 2 pi square root of L over G. Okay, so we want to solve for that acceleration due to gravity, G. Okay, so let me do this in a couple of steps. We're going to divide by this one, divide by T, multiply by the square root of G, and we should get 2 pi square root of L times T. Square both sides, we get G equals 2 pi squared times L times T squared. Okay, so our acceleration due to gravity should be 2 pi squared times our length, which is 0.75 meters, times our period, 1.7357 seconds. Okay. Now, oh, whoops, that should be divided by. It's always the little things. Okay, so this should be 2 pi square root L over T, and then this should be 2 pi squared L over T squared. Okay, so let's go ahead and put that into our calculator. (1.7357) squared. And we get, believe it or not, 9.828, how many digits is this? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 meters per second squared. So now this is our acceleration due to gravity in this region. Okay? And notice that that is similar to our known 9.8 meters per second squared. Okay, so this checks out. Okay, let's go ahead and stop this video here, and then I'll continue in the next one.